Yeah, that clock keeps ticking till we start up in here. Yeah, that clock keeps ticking till we start up in here. If you came to learn chemistry, you did your part. Time is ticking down, so just be ready, cause it's about to start. When we solving for problems, we solve it information. You know Ben's Chem videos will provide you with equations. Never have to stop and think about it, this the station that will provide you with the chemistry all in relation. If you came to learn chemistry, you did your part.
Hello everyone and welcome to the Ben's Chem Videos Sunday night live stream. Tonight we are going to continue with our discussion on electrochemistry. So really excited about that. I think it's going to be a great show. I apologize for my absence last week. I was pretty sick. Yeah, I actually had to burn 2 days off of work. I had to take 2 consecutive days off of work because I just couldn't get out of bed. And yeah, it was pretty bad. I haven't had to do that in a very long time. So all right, so I think we are all set to get going. So without further ado, I present to you Electrochemistry Volume 3. As always, your feedback is more than welcome and highly encouraged, so please feel free to drop your thoughts, concerns, questions, what have yous in the chat if you're watching this live. And if you're watching this in the form of a video, please feel free to leave me a comment, because without your feedback, I am completely and totally lost. Also, if you're watching live, you can call into the show. I have Discord. There's a link in the description for you to call into the show via Discord if that's something you're interested in. I would love the opportunity to have a voice-to-voice discussion with you. I think that'd be really cool. So all right, we are going to kick things off by reviewing the content from Volume 2. So basically, what have we learned so far, right? Well, we have learned that redox reactions, oxidation-reduction reactions, when they are configured a certain way, they can generate electric current, right? And the configuration or the device that makes this possible is called an electrochemical cell. And remember, with electrochemical cells, there are 2 main types. There's the voltaic or galvanic cell, and then there's the electrolytic cell. The main difference between them being that in a voltaic cell, you have the production of electric current. Electric current is produced from a spontaneous redox reaction. And then on the flip side, with the electrolytic cell, you have electric current being consumed in order to drive a non-spontaneous redox reaction. And one of the big things that we did last time was we looked at a diagram of a voltaic cell, right? Just to understand how it works, right? So we spent quite a bit of time on that, and there's a lot of stuff in there. So I think it'd probably be worthwhile for us to go through that again briefly. So here's the diagram of the voltaic cell. I'm going to get my head out of the way there. Actually, you know what? What I'm going to do is I'm going to take you guys to the whiteboard so I can kind of draw and sort of annotate this thing and follow along. So bear with me. We're going to go to the whiteboard real quick. I've already got the image up here. So basically, an electrochemical cell, in this case a voltaic cell or galvanic cell, is composed of 2 main components called half cells, right? And each half cell consists of a strip of metal submerged in a solution. In this particular voltaic cell, we've got a strip of zinc immersed in a solution of zinc ions. That's one of our half cells. And then in the other half cell, we have a strip of copper submerged in a solution of copper ions, right? So we have the oxidation of zinc to zinc 2+, and then we also have the reverse of that occurring, right? The reduction of zinc 2+ into zinc, right? It's an equilibrium process, right? And you have the same thing going on with the copper. The copper is being oxidized to copper 2+, and you also have the reduction of copper 2+ to make just copper, right? So we have 2 equilibrium redox reactions occurring, right? However, remember, the position of the equilibria for these 2 metals are not the same. Zinc has a much greater tendency to ionize than the copper does, right? The position of the equilibrium for the zinc oxidation lies further to the right than it does for the copper reaction. And yet again, a third way of saying this would be that the equilibrium constant associated with the oxidation of zinc has a larger value than the equilibrium constant for the oxidation of copper. And so something very interesting happens when we connect the zinc strip to the copper strip, right? What happens is that these metals start to act as electrodes, right? Remember, electrode, that's just a conductive surface that allows electrons to either enter or leave the half cell, right? So when these two strips of metal submerged in these two solutions are connected together, what's going to happen is electrons will spontaneously flow out of the zinc and toward the copper, right? Electrons spontaneously flow from the zinc to the copper. And again, that's because zinc has a greater tendency to ionize, to undergo oxidation than the copper does, right? And so if you think about, again, we have two reactions at equilibrium, right? What's going to happen when we disturb the equilibria of these two reactions by having electrons flow from the zinc to the copper? Well, if we look at the zinc for a second, right, what's happening is the electrons are leaving the zinc electrode. So you have that you're removing electrons. So what's that going to do to the equilibrium? Well, that's basically going to stimulate the production of more electrons, right? When an equilibrium is disturbed, right, the reaction is going to react in a way that opposes the disturbance, right? So when you're constantly removing electrons, that's going to stimulate the production of even more electrons. And so the zinc will continue to undergo oxidation, right, to pump out more electrons that are constantly being lost by this electrode here, right? And then if you look at the copper, well, the copper has the opposite problem, right? It's gaining electrons. It's being inundated with electrons. And so that's going to shift the equilibrium toward reduction of the copper ions into copper, right? And remember, there's a couple of terms that we talked about, right? There's the electrode where oxidation occurs. That in this case, that'd be the zinc electrode. That's called the anode, right? That's the anode. And then the other electrode where reduction is occurring, in this case, the copper, that's called the cathode, right? So we have a spontaneous flow of electrons from the anode to the cathode. And again, it all originates from the thermodynamics of the equilibria of these two reactions, right? The zinc electrode, or the zinc reaction rather, has a much greater tendency to ionize. It proceeds to the right, so to speak, right? Okay, now another very important component of the voltaic cell is this thing right here. This is called the salt bridge, right? And so basically what happens is as the electrons continue to leave the anode, what's going to happen is positive charge is going to build up in the solution of the anode, and in the cathode, you're going to have a buildup of negative charge. And so what the salt bridge does is it allows ions to come in and neutralize the charge buildup in the solutions, because if you didn't have ions coming in to neutralize that charge buildup, then the flow of electric current would stop almost immediately. So that basically just allows the process to continue, right? So we talked about that. Hopefully this is kind of like a review. Hopefully, nothing is like a new revelation here. So let's go back to the PowerPoint. We continue this review, and then we'll move on. So back to the PowerPoint. How's everybody doing tonight? Not a rhetorical question. I really want to know what your thoughts are in the chat. Let me know how you're doing. I want to know. All right. So to continue our review, right? Let me move myself back in position here. So we talked about the components of a voltaic cell and how it works. And we also started talking about some properties associated with voltaic cells, right? There's a property called potential difference, right? And potential difference is like the driving force. It's like the reason why electrons will flow from the anode to the cathode, right? And as the name implies, potential difference is simply a difference in potential energy per unit charge across the electrodes. And it's very similar or very analogous to the difference in gravitational potential energy in a stream bed, right? The water in a stream is going to flow from higher to lower potential energy. So it's kind of a similar sort of difference in potential energy, only we're talking about electrochemistry here, right? And the other name for potential difference is called electromotive force. I really like that name because it just kind of drives the point across that it is a driving force that drives the redox reaction that causes it to occur. Now, in a voltaic cell, potential difference goes by the name of cell potential, or it could also be called cell EMF, cell electromotive force, right? And cell potential in a voltaic cell depends on a couple of different factors, right? It depends on the relative tendencies of the reactants to undergo oxidation and reduction. It also depends on concentration, and it also depends on temperature, right? And so if we wanted to normalize it by concentration and by temperature and only focus on the relative tendencies of those reactants to undergo oxidation and reduction, then we have something for that called standard cell potential, which is simply the cell potential, the potential difference, the cell EMF at standard conditions. Remember, standard conditions is like 1 atmosphere for a gas and 1 molar for an aqueous solution and this and that. So it kind of just standardizes everything so we can really get an apples to apples comparison between cells, right? And so what makes standard cell potentials different from one cell to another is the fact that these different metals, these different substances have different tendencies, right, to undergo oxidation and reduction. And so depending on which 2 metals or which 2 components you have, which 2 half cells you have, that's going to result in different values for your standard cell potential. And finally, the last thing we did in volume 2 was we talked about electrochemical cell notation. It's that line notation, right, where you always have your oxidation half reaction on the left and your reduction half reaction on the right. They're separated by a double vertical bar. And then you have substances that are in different phases separated by a single vertical bar. And then you have substances that are in the same phase separated by commas. And if you're interested in learning more about that, you can always refer to volume 2. By the way, all of these episodes you can find conveniently located in a playlist called Electrochemistry Livestreams. Link is in the description. So, all right, I think we're ready to move on and talk about tonight's material. Really excited about it. So what are we going to talk about tonight? Well, the main idea of what we're talking about tonight is that we can think of each half cell within a whole cell. We can think of each individual half cell as having its own individual electrode potential, right? And these are called standard electrode potentials, right? And so to get a better understanding of this, we're going to make a little analogy here, right? So imagine that we have something like this where we have 2 water tanks, as I get myself out of the way here. So imagine we have these 2 water tanks, right, with different amounts of water in them, and they're connected by a common pipe. What do you think is going to happen when we open the pipe and connect these 2 tanks of water together? It's pretty intuitively obvious, right? Water will flow from the tank with more water. In other words, that the water is higher up, right? So it has a higher gravitational potential energy. Water is going to flow from the tank with the higher potential energy to the tank with lower potential energy, right? And there's a similar thing that happens, right? Just like we can measure the height of each of these tanks of water, we can measure the electrode potential of each individual half cell within a voltaic cell, right? Now, one problem that kind of pops up when you're trying to measure individual half cell potentials is that you can't directly measure individual half cell potentials, right? You can only measure the cell potential of a whole cell, right? When 2 half cells are connected together, you can't measure just one, right? So how do we solve that problem? Well, one way to solve that problem is by assigning a value of 0 to a particular type of electrode, a particular type of half cell, right? And then we can measure the electrode potential of other half cells relative to the 0 that we defined, right? So let's talk about the electrode that is most commonly given a value of 0. And that's called the standard hydrogen electrode, or SHE for short. When I was first studying this stuff, I always just called it the SHE. I don't know if anybody else uses that term, but that's what I called it when I was sort of reading this stuff in my head way back when. Standard hydrogen electrode. So what is going on with this half cell? Okay, so basically what this half cell is it is an inert platinum electrode, right? It's a piece of platinum that only functions as an electrode. It's not undergoing oxidation, it's not undergoing reduction, it's not participating in the redox reaction. All it's doing is just functioning as an electrode, a conductive surface that allows electrons to enter or leave the half cell. So you have an inert platinum electrode, right? And it is submerged in a 1 molar solution of H plus ions. So typically it'll be like HCl or something like that, 1 molar HCl, right? So a 1 molar solution of H pluses. And then you have hydrogen gas at a pressure of 1 atmosphere being bubbled through this solution, right? So this is your standard hydrogen electrode. And up here, this wire up at the top, that's where you would like hook it up to another half cell, right? So if your standard hydrogen electrode is acting as your cathode, right, the electrode where reduction occurs, then this is the reduction half reaction associated with that process, where you have H pluses gaining electrons to become just plain old hydrogen, right? And so this is the value of 0 that we're looking for, so that we can, whenever we hook up something, right, whenever we hook something up to the to the standard hydrogen electrode, we can measure the half cell potential of it, the electrode potential of it, because we know, because by definition, this half cell potential has a value of exactly 0 volts, right? So let's say, let's just suppose, right, that we hook up the zinc electrode to the standard hydrogen electrode. And again, I have to move myself out of the way. I think I'll just stick myself between the two half cells here, because I don't really, actually, no, I think up here in the top right-hand corner is probably a better place to put myself. Okay, so what would happen if we connected the zinc electrode under standard conditions, of course? By the way, until I say otherwise, I'm basically just going to be talking about standard electrodes, standard conditions, right? 1 molar solutions, 1 atmosphere for gases, and so on and so forth. So if we have a strip of zinc, right, submerged in a 1 molar solution of zinc ions, and that was our other half cell that we connect to the standard hydrogen electrode, and let's say we have a voltmeter up here so that we could actually measure the cell potential, then under standard conditions, that value is going to be 0.76 volts, positive 0.76 volts, right? And so since we have a positive value of our standard cell potential, that means that this process will occur spontaneously. Electrons will spontaneously flow from the zinc electrode to this standard hydrogen electrode, right? And also, since we know the measured standard cell potential, right, 0.76 volts, and we also know the half cell potential of the standard hydrogen electrode, it is 0 by definition, right? Then we can use that information to calculate the standard electrode potential for the zinc electrode. So if we do the math, it sort of breaks down like this. Let me move myself out of the way again here. So if we do the math, it kind of breaks down like this, right? So we can consider the standard cell potential as being like the difference of the cell potential in its final state minus its initial state, right? Now, since electrons are flowing from the anode to the cathode, right, that means that the half cell potential or the electrode potential of your cathode would represent the final state, and the electrode potential of your anode would represent your initial state. And so we arrive at this second formula here where we have E cell is equal to E cathode minus E anode, right? And so the cell potential, which would be measured in this case, right, 0.76 volts is equal to 0.00 volts, right, which is the electrode potential of your standard hydrogen electrode minus the standard electrode potential for your anode, in this case, that zinc electrode, right? And so if we rearrange this equation and solve, we're going to get that the standard electrode potential of our zinc electrode has a value of minus 0.76 volts. Notice that it's negative, right? That's very, very significant, right? What this means is that the electron in the zinc electrode has a greater potential energy than an electron in the standard hydrogen electrode, right? So if we refer back to that water tank analogy that we were talking about earlier, right? So imagine that the standard hydrogen electrode is like a water tank filled to here, right? The zinc electrode would be analogous to hooking up a water tank with a much higher water level, right? So that means that, again, it just means that an electron in the zinc electrode has a higher potential energy than the electron in the standard hydrogen electrode. So basically that means it's an energetically downhill process. It'll occur spontaneously, right? Now imagine that we took that same standard hydrogen electrode and we hooked it up to a copper electrode, right? So let's say we have, a strip of copper submerged in a 1 molar solution of these copper ions here, and we measure the potential, right? Everything's under standard conditions. If we were to do that, we would end up with a value of negative 0.34 volts. Negative 0.34 volts, right? So if we have a negative value of our standard cell potential, that means that this process will not occur spontaneously. We will not get a spontaneous flow of electrons from the copper to the standard hydrogen electrode, right? So again, if we take that same approach that we used for the zinc electrode to solve for the electrode potential or half cell potential of the copper electrode, then it's going to break down like this, right? So you have E cell, your standard cell potential is going to be equal to 0 volts minus the electrode potential for your anode, right? In this case, E cell is minus 0.34 volts, right? So if we rearrange and solve, we're going to get the standard cell potential, or standard electrode potential for the copper. It's going to come in with positive 0.34 volts, right? It's positive, right? So what does that mean? That means that an electron in this copper electrode has a lower potential energy than the electron in the standard hydrogen electrode, right? Lower potential energy. So if we refer to that water tank analogy, right, the copper electrode would represent a water tank with a lower water level than the water level of the standard hydrogen electrode water tank, if that makes sense. I hope I haven't lost everybody just now. But so yeah, if you have a positive value, right, a positive value of your electrode potential, that means that an electron within that electrode is going to have a lower potential energy than an electron that is in your standard hydrogen electrode, right? And so if we look at these two electrode potentials side by side, right? The zinc and the copper, right? So by convention, electrode potentials are always written with respect to the reduction half reaction, right? So both of the reduction half reactions are shown, right? So here's the reduction half reaction for reducing copper, and then down here is the reduction half reaction associated with the reduction of zinc ion to make zinc, right? So remember, with the copper, had a value of positive 0.34 volts. For the zinc, had a value of minus 0.76 volts, right? So that means that if the zinc is your anode, the flow of electric charge will occur spontaneously because it has a higher potential energy than the standard hydrogen electrode. If, on the other hand, you were to swap out that zinc electrode for a copper electrode, then electrons will not flow spontaneously, right? Because that means an electron in the copper electrode has a lower potential energy than that of the standard hydrogen electrode, right? And so somewhere in your chemistry textbook, there is a table, and I'm going to find the version of the table that I have and show it to you. Let's see if I can find it here. So my PowerPoint is kind of in the way. Let me get rid of that right here. Okay, so this is it, guys. This is it. Okay, so this is a table of standard electrode potentials for a variety of different substances. And so you can see here that we have the reduction half reaction that is shown. I hope this is big enough, and I hope you guys would let me know if you couldn't read this. I think it's big enough. I think I'm zoomed in enough here, right? So we have the reduction half reactions that are shown here, and then we have their corresponding values of their electrode potentials measured in volts, right? And this table is arranged such that the substances with the greatest tendency to undergo reduction, right? In other words, the best oxidizing agents are listed at the top, and the lousiest oxidizing agents, in this case, like lithium, right? That would represent a really, really lousy, really weak oxidizing agent. Those are located toward the bottom, right? So we know that lithium ion is a terrible oxidizing agent. but lithium metal is a really, really good reducing agent. So that's kind of how this table works. And we're going to use this table a little bit more as we go forward. So I'm going to take you guys back to the PowerPoint here. And I think what we're going to do next is we're going to solve a problem. So let's see if we can get to the problem. Hey, I got a super chat. Dude, this is like the first super chat I've gotten in like 7 streams or something, man. Andrew Kyle Bart, thank you, man. Says, great teaching, Ben. Keep up the amazing work. I surely will. And just that super chat goes a long way to like motivate me further, man. I appreciate it, dude. You're the best. All right. So here's the problem. So let me let that text go away from the screen there. So the problem says to use tabulated standard electrode potentials to calculate the standard cell potential for the following reaction. And the reaction is shown down here where we have nickel and lead 2 ion, Pb2+, reacting to form nickel ion, Ni2+, and just plain old lead, right? So what I'm going to do is I'm going to copy and paste this problem into the whiteboard, and I'll show you guys step by step how to solve it. So bear with me while we go into the whiteboard. Delete that, no longer need it. Okay, there we go. I'm gonna resize it, make it nice and big so we can see what is going on. All right, how's everybody doing tonight? I hope you guys have had a great weekend, and I hope you were all geared up to have an amazing, wonderful, safe, productive week. I really do. Not a rhetorical question. I really want to know. Type it up in the chat. Let me know how you're doing. All right. So basically what we need to do is, again, we're using those tabulated values of standard electrode potentials to calculate an overall cell potential, right? So the first thing we need to do is we need to identify what's undergoing oxidation and what is undergoing reduction, right? So it looks to me like nickel, right? Nickel is being oxidized. It's losing electrons. And lead, the lead ion rather, is being reduced to just plain old lead, right? So I'm going to write these two half reactions out, okay? So I'll start with the reduction half reaction. So that looks like this, where you have Pb2+ and 2 electrons reacting to form just plain old lead, right? So that would be your reduction half reaction. And then your oxidation half reaction would look something like this. So you have nickel being oxidized, right? So you have your nickel Ni reacting to form Ni2+ and 2 electrons, right? So now that we've sort of separated our oxidation and reduction half reactions, now we can simply refer back to our table, right? We can refer to our table and we can identify which half reactions they are, locate their values of the electrode potential, and then use the formula for how to calculate electrode potential, which we saw a few slides ago, to solve for the standard cell potential, right? So if we go back to, let's see if I can just take you guys back to the table real quick. So we have the reduction of lead ion, and we have the oxidation of nickel, right? So let's see if I can find those in my table here, right? So let's start with the reduction. So we're looking for the reduction of Pb2+ to just lead. So kind of a long table. See if I could find it. Hopefully I could find it pretty quickly. Looks like we found it right here. So the reduction of lead 2+ to form lead, that has a standard electrode potential of minus 0.13 volts, right? So I'll take you back to the whiteboard real quick. 0.13 volts. And again, that's the reduction. That's the cathode, right? The cathode, that's the electrode where reduction occurs, right? So we have E for our cathode is equal to, what did I say? Minus 0.13, I think is what I said. Yes. Okay. Now let's find the corresponding value for the anode. So I'm going to have E anode, right? So what is that? So let's go back to our table, once again, we can figure that out. So we're looking for the reduction half reaction equation that corresponds to the reverse of the oxidation of nickel, right? So which one has nickel? It looks like it's this one right here, Ni2 plus 2E negative equals just nickel. So again, by convention, it's the reduction half reactions that are shown, but again, we're looking for the reverse of the oxidation of nickel. So that's located down here, and that looks like it has a value of minus 0.23 volts, right? So we have minus 0.23 volts, right? Let me go back into the whiteboard. Right now I'm on my screen there. Okay, so let me sort of shrink this down so I can get everything there. Okay. All right, so we're doing pretty well so far, right? We have our standard electrode potentials of our cathode and our anode. At this point, really all we need to do is just plug them into that formula. So hopefully we remember the formula, but if not, I'll go ahead and remind you what it is. So we have E standard for the cell is equal to the standard electrode potential of a cathode, right? Because that's considered like the final state, right? Because electrons flow from the anode to the cathode, right? Minus the standard electrode potential for our anode, right? And so numerically, what's that going to be, right? Well, for our cathode, it's minus 0.13 volts minus the same thing for our anode, which is minus 0.23 volts. So we have minus negative 0.23 volts, right? So minus a negative, that's the same as plus, right? So really what we have is positive 0.23 minus 0.13. And the value that I ended up getting is positive 0.10 volts, right? So our standard cell potential in this case, positive 0.10 volts. Remember that since our cell potential has a positive value, that means that this process is spontaneous as written. Electrons will indeed flow from the nickel to the lead in this case. If it was negative, it wouldn't happen. So it's important to remember that. All right, guys, so we got a couple more things to look at before we are all wrapped up with the educational part of this live stream. So it looks like I'm going to end this poll. 83% of the people that I asked how you were doing said they were doing well. 17% said not well. I certainly hope that the not well crowd, I hope things turn around for you. I really do. I'm going to go ahead and end that poll, and we are going to move on. So let me go back into the PowerPoint real quick. And we only have like I said, we only have a couple more things to do here. And then we'll be pretty much done. This is going a lot faster than I thought I would. I probably should have prepared more content. All right. So now what we're going to do is we are going to do a nifty little thing using the table of electrode potentials that we saw just a few moments ago. And we are going to predict the direction of spontaneity of a redox reaction, right? So if we are given two half cells, right, one designated as our anode, one designated as our cathode, right, we want to predict whether or not that redox reaction will occur. Will the electrons actually flow out of the anode and into the cathode, right? And as you can imagine, it depends almost entirely on the standard electrode potentials for the anode and the cathode, right? And so let me refer back to the table of standard electrode potentials for a moment here. Let's see if I can find it. So here we go. All right. So again, this is our table of standard electrode potentials. And remember, right, the table is organized such that the strongest oxidizing agents, the substances with the highest tendencies to undergo reduction, are located at the top, and then it goes in descending order, right? And so one way that you can tell whether a redox reaction will be spontaneous or not is to simply look at the relative positions of the reduction and oxidation half reactions in this table, right? If you have, let's say, just pick one of these at random, right? Any one of these reduction half reactions. Pick one of them at random. Any reduction half reaction is going to be spontaneous if you connect it to the reverse of a reduction half reaction located under it in the table, right? Let me say that again. Any reduction half reaction will be spontaneous when paired with the reverse of a reduction half reaction below it in the table, right? So if I look up here, let's say I want to look at this this one right here, the reduction of chlorine into chloride ion, right? If I pair this half cell up with the reverse, with the oxidation half cell of any of these substances listed below the reduction of chlorine, then that will be a spontaneous reaction. That would ultimately result in a positive value for your standard cell potential, right? So it's a pretty cool position to be in, where all we have to do is just look at this table, look at the relative positions of our reduction and our oxidation half reaction, and just by knowing where they are, right, is the oxidation half reaction located below or above your reduction half reaction, you can tell whether or not it's going to be spontaneous. And so in the next slide, we're going to get into that. We're going to do a couple of problems where we predict the direction of spontaneity just by looking at the relative positioning of the half reactions in this table of standard electrode potentials, right? So this is the problem. So it says, without calculating the standard cell potential, determine whether the following redox reactions are spontaneous as written. And by spontaneous as written, what I mean is, are they spontaneous in the forward direction, right? Because if something's non-spontaneous in the forward direction, that means it's spontaneous in the reverse direction. So I want to know, are these reactions spontaneous as written? Are they spontaneous in the forward direction, right? So this first one here, we've got nickel plus zinc ion yields nickel ion plus zinc. And then the second one here, we have silver ions and nickel reacting to form silver and nickel ions, right? So let's look at these, right? Let me just copy and paste this into the whiteboard. I think I'm probably going to want to scribble a little bit here. I got another super chat. Oh my goodness, that is amazing. Dude, I've been so long without a super chat, and then I get two of them. Man, you guys are great. Darwin Hev says, love your videos, Ben. Second exam is 3 more weeks for organic chemistry. Best of luck to you, sir. I know since you watch this channel, obviously you're really, really smart. I know that you will nail that exam. And I think I speak for everybody in the chat, all of us. We are all rooting for you. So let's give Darwin our utmost support as he prepares to crush his organic chemistry exam. All right, let's go to the whiteboard and do this problem. Then we're going to be pretty much done for the night. So let me delete all that stuff that we no longer need. Okay, here we go. Here we go. All right. Okay. All right, so let's look at this first one, right? We have nickel, we have zinc. So again, the first thing we need to do is we need to identify what's being reduced, what's being oxidized. It looks like zinc ions are gaining electrons. They are being reduced to just plain old zinc. And it looks like nickel is being oxidized. It's losing electrons to form the nickel 2+ ion, right? So let's locate those in the table. We're looking at the reduction of zinc ion, and we're looking at the oxidation of nickel, right? So let me take you guys back to that table and see if we can find it. So again, we have the reduction of zinc ions, and we have the oxidation of nickel, right? So let's locate the reduction of zinc ions. Let's see if we can find it in this table. Where is it? Where is it? I don't see it. Oh, here it is, down here. Okay, so we have Zn2+ plus 2 electrons yields zinc. That has a value of minus 0.76. Again, we don't really care about the value at this point because we're just trying to predict whether it's spontaneous or not, right? Really, the question is the reduction half reaction for the reverse of the oxidation which is going on, which is the oxidation of nickel, right? So is the reduction half reaction associated with nickel higher or lower than the reduction half reaction for the reduction of zinc ion, right? It looks like it's higher, right? So here, up here, we see the reduction half reaction for the reduction of nickel, again, which is simply the reverse of the oxidation of nickel, right? And the rule is any reduction half reaction is going to be spontaneous when paired with the reverse of a reduction equation below it in the table. Since this equation up here for this half reaction is above the half reaction associated with the reduction, then I'll take you guys back to the whiteboard. That means that this will not occur spontaneously, not in the forward direction, right? Let's look at the second one, right? So we have, again, first thing we need to do is to just identify what's being oxidized, what's being reduced, right? It looks like the silver ions are being reduced to make silver, and it looks like the nickel is undergoing oxidation to become the nickel ion, right? So we have the reduction of silver ion and the oxidation of nickel. Reduction of silver ion and the oxidation of nickel. So what does that look like in the table? Let's see if we can find the reduction of silver ion. Looks like I have found it right here. So we have this Ag plus an electron, right? So that's located up here, right? So the $1 million question is the oxidation of nickel, is the reverse of the oxidation of nickel below or above the reduction of silver in this table? And if we scroll down here, we can clearly see that nickel lies below silver in this table, right? And since any reduction half reaction is going to be spontaneous when it's paired with the reverse of a reduction half reaction below it in the table, that means that, yes, this will be spontaneous. It'll be spontaneous in the forward direction. So there you go, guys. That is how to predict the direction of spontaneity simply by using that handy dandy nifty table of standard electrode potentials. All right, guys. I need to remember to turn that music off. I always forget to turn the damn music off. I don't know. But all right, guys, that is going to do it for tonight. Again, if anybody wants to stick around and chat about whatever you guys want to chat about, perfectly happy to do that. Get to know you guys a little bit better. I think that'd be cool. But that's going to do it. Thank you guys so much for watching. For those of you who sent your support in the form of super chats, mwah! Thank you guys so much. Really, really, really appreciate the support, especially after last week. I was sick. I couldn't stream. So to come back to this level of support and engagement, I have no words. I'm speechless. It's wonderful. So I hope that this stream provided some value to you. And I would also sincerely hope that I will see you in the next one. There's certainly a lot more electrochemistry stuff to talk about. So I hope that you are as excited about it as I am. All right, guys, take care. Have a good night.